DIFC, workbook and slides, physics, mechanics, and we did this one last time, so this one now today. Okay. There we go. Moment and center of gravity. You can write this down. Got that? Yeah. Okay, let's have a look. So, got that, Siva? Yep. Okay. Matt? Got it? Okay. Moment and center of gravity. So, lots of pictures in this one. Yeah. Firstly, actually, does anybody know what the center of gravity is? Have you heard of this before? Yeah. What would you say it is? Do you know?
Where the object feels the most gravity? More stable?
Yeah, no, you could relate it to stable. Yes. How exactly? What would you say? You're kind of close with the most gravity as well. That's another way to think of it. It's not quite most gravity. It's a different word than most gravity. Yeah, it is. Okay. So the center of gravity of an object is the single point to which the full weight of a body appears to act. So I think this is what you were trying to get at, was it? Yeah. It's the point where the weight appears to be acting from. Okay, you got that? Yeah. So basically, it's where the weight force factor acts. So if I was to try and draw a picture of it, there we go. Like, here's a mass. There's a point here where the weight acts. So we call that the center of gravity, that point where it acts. And you realize it depends on how the object mass is spread out. It's kind of like an average point. So for example, if I draw something like this, do we expect it to be nearer to the left or nearer to the right?
Right.
Yeah, now why?
Because there's more mass on it.
Yeah, so we kind of imagine it over here rather than here.
Mm-hmm.
Yeah, and we certainly don't think it's here. We can't really picture that. So this is what I mean by it's kind of like an average. Whoops, sorry. An average point. So where there's more mass, right? Where there's more mass, this is where sorry. Where there's more mass, this is where the center of gravity should be. Yeah. Are we okay with this? Here's an example of three people. You can see their center of gravities, okay? There, there, and there. Why is this one a little bit higher? The boy on top. And why is his one not in the middle, where his stomach is?
Because the bag.
Because the bag, yeah. Yeah, and hers is a little bit forward because of the books, right? Of the three of them, who's the most likely to fall?
This one.
Yeah, why?
Let's stay calm.
Yeah. You see, when the centre of gravity is quite high, it makes it easier for something to fall. So like this here is easier for me to push over than say this cup. Okay? But you know this with cars, you know? If the car is very tall, when it turns, what is likely to happen if it turns too fast?
Go on 2 wheels.
Yeah, go on 2 wheels, and then if it turns too fast, it'll flip. Yeah. So like what type of car is this a problem for? SUV is this a problem for. Yeah. So the centre of gravity being higher makes it more likely to fall. Yeah. So before we continue, we need a little bit more vocabulary. So we have this word called fulcrum, which is actually just another word for. I wonder if anyone knows. Anyone seen this word before? Fulcrum? No. No. Nobody? Are you sure? Are you 100% sure? Okay. Fulcrum is another word for a turning point. Or another word for a turning point, we've got 3 words here that mean the same thing, is a pivot.
I heard that one.
You heard of pivot? Yeah, okay. Got that?
Mm-hmm.
Yeah. And what do you think it is? Like, what is a turning point or a fulcrum or a pivot? Like, if you think about the word turning point, well, what do you think I'm trying to describe? Yeah. It's like that point, isn't it? It's the point where the object turns. So, for example, the hinge on a door. So this here, you know, that's called a fulcrum, or a turning point, or a pivot. That's what you call that there. Okay. When I'm walking, okay, you can see when I put my foot on the ground, there's like a turn. So this here would be the fulcrum. Yeah. So the hinge on a door is an example. The center of a seesaw with the children sit on. The wheels on a car, where the wheel is on the ground turning, and your foot on the ground when you're walking. These are all fulcrums. Okay. So just write down this definition, and then we'll continue. Have we got this definition? Yeah. Okay. Right. So notice how the ballerina, the center of gravity is above the turning point. It's around about here, right? But she is more likely to fall because there's another problem she has. Okay, so one problem is the center of gravity is up here. There's a second problem that will make her likely to fall. What's her second problem?
Area.
Yeah?
Surface area.
Yeah, surface area of what exactly?
The bottom.
No, not quite. Well, what do you mean precisely?
Like her hands basically.
Her hands basically, yeah. The area is quite small, you know. It's kind of like, tell me which is worse. If you have something like this, you know, and here's the center of gravity here, or if you have something like this. So, the center of gravity is the same, isn't it? But which is more likely to fall? The second one. And the reason is because of what you were saying here, the area. Yeah? So, she could easily topple. She could easily fall. Now, what I need you to write down is this term, very unstable. So, if you want to picture it like a definition, very unstable, you need 2 things. center of gravity is above the fulcrum and the contact area is small. That's kind of what I have in this picture here. Can you look up for a sec? This here is the fulcrum, yeah? And this here is the center of gravity. And you can see that it's higher than the fulcrum. And also the area is small. So you have these two things. The COG is above the fulcrum and the area is small. That's what's very unstable. If you can make note of this. So, if you look at me, I'm standing here. Am I, would you say I'm very unstable? No. I mean, I look stable, but I actually am very unstable because my feet are quite small compared to the rest of me, right? So why don't I easily fall down? What's keeping me standing? Oh yeah, but still, I could easily just fall down. Like, why am I not falling down right now?
No, wait.
Oh, it's close.
Your center of gravity?
Well, my center of gravity is like here.
Yeah.
So.
But like it's downwards.
You have to like.
I know I can actually still do pretty well on one, you know. What do we think?
Force.
Yeah, what force?
Wait.
Gravity?
No. So,
Drag.
no. And the reason I don't fall, you know, that I could do something like this, is because I have a brain. You see, it kind of maybe what you were getting at with force. I'm able to balance, readjust, okay? You know, you really have to think about this. When you see a robot, it's very difficult to make a robot walk on two legs. Because it's easy for the robot to fall, okay? Because what your brain is doing to balance you is actually quite difficult. Because your feet are so small, you know, you should fall. Like when you think about most animals walk on four legs, don't they? Dog, a cat, you know. So because the human brain is so big, it's able to do things like, you know, balance like this. Like you might say a bird can walk on two, but birds have wings to balance if needs, so it's not quite the same. Okay, so that's the ballerina. The next one is just simply unstable rather than very unstable. So what's better in this picture?
What's what?
What's better in this picture?
Has a bigger contact.
Yeah, the area is bigger. But could it fall? Of course it could fall. You've all spilled coffee before. So we say it's unstable if the center of gravity is above, but the area is bigger. Okay, so if you want to write that down. So the center of gravity is above, but the base is kind of big. So you can write it in this structure if you want. Center of gravity above, contact area is big. That's the only difference, okay? So if you make note of that somewhere. Okay, you got that? So the next one I'm going to show you is a toy that maybe some of you had as a child. Anybody ever seen this toy? You seen this before? It's the bird that balances on your finger. You've seen this? Yeah? No?
Yeah.
You know this toy? Yeah.
But
So
it didn't have like the thing, or was this its mouth?
no wings?
It did have wings, but this thing, the
Tail?
No, the other side.
Yeah.
The other side. There's like a line.
A line?
Yeah.
Where?
The other side. The other side on the left. Yeah, this one.
That's its wing.
I know it didn't have it. Without the foot.
Oh, okay, anyway. This toy, it's a toy bird, and you can put it on your finger and it balances there. And the way they designed the bird, it's quite interesting actually, so I haven't seen it in a long time. They made the bird, how can I try and draw this? There's its head, there's its beak, there's its body, and there's its wing like this. So they made the bird so that the center of gravity is right here. The center of gravity is right here. So if you put your finger there, also right here is the fulcrum. So the two of these are at the same point. So it's kind of weird. It's called neutral. It means the bird will stay there, but you can still kind of move it, but it kind of moves around a little bit. But it doesn't fall. It's kind of all balanced. We call this one here neutral. So this is the center of gravity is at the turning point, the beak. So even a little force may make it move, but it shouldn't fall off. So you could maybe hit the bird and it might move a little bit, but it shouldn't really fall off. Now if you hit it hard enough, you can knock it off. So for this neutral one, the key thing, the absolute key thing, is that the center of gravity and the turning point are at the same place. That's what makes it neutral. Got that? Yeah? Yeah. So who's seen this toy before? Just you? Are you seen it? Did you have one?
Yeah.
Yeah.
I have one.
You have it at home in China? Or?
No.
No. Okay, now this next one is called stable. And this is when the center of gravity is below the turning point. And the reason we call this stable, okay, obviously if he lets go, he falls, but let's pretend he doesn't let go. We call this stable because if I knock it, does it fall down? No, it just stays hanging there, But this one is unstable because if I knock it, it falls down. Okay, but this guy, he doesn't fall down. I can knock it and it just swings and then it'll go back to normal. So we call this position stable. This is when the center of gravity is below the turning point. That's called stable. Okay. So if you can make note of this, please. Got that? No. Okay, next. Yeah? So the next one is very stable. It's the same center of gravity is below the turning point, but you have a very great contact area. So this door is not going anywhere. Every time the cat and dog go through the door, it always goes back to the same position. Okay, it's not going to fall. It's very stable. So it should never fall. You got this? Yeah? Okay. Next now. Right, so we've been talking a lot about centre of gravity, and we need to move on to something a little bit different, but kind of related. This thing we call the moment of a force. So, I'll try and draw a little picture here maybe. These pictures are different. So, let's see, we'll draw our stick man. He's lifting something up here. So he's trying to pull this up, okay? Or he could do this. So you see what he could do. Oh, sorry. He could push down here to make this one move up. Now these ones are a little bit different. This one here, this is just normal. This one here is just normal force, okay? But this one is kind of like a turning force, because he's trying to make this turn this way, so this side can turn that way. This is a little bit different than him trying to pull up to make the block go up. It's not quite the same, okay? So we don't call this force. Instead we call this the moment of a force, which is the force multiplied by the distance. So here in this picture, if this, I'll draw it here for you. If you push up here with F, and this here is D, we say the moment is the force multiplied by the distance. That's the moment. It's like a special type of force. It's like a turning force. So the definition is force multiplied by the perpendicular distance. It's basically a turning force, and another word for it is moment or torque. And it's a formula, it's like this, F times D. The units, of course, are Newton meters. Sometimes tau or gamma is used instead of L. I think I'll try and stick with using L. Now I'll explain this a little bit more. Got that? That's okay.
Is the J joules?
No. Actually, you know what? I think I want to get rid of the J. Just forget about it. I'll never use the J. So I'll just get... Yeah, I'll never use the J. But I sometimes use this letter or this letter. I really need to try and stick with just one letter. Maybe L. I need to check what A-level physics books use. Can I continue? It measures how much of a turning effect there is. So a big moment means there's a lot of force trying to turn the object. So look, I'll explain this in more detail. So you can see here the man lifting the planet with a great turning force. But I think you kind of have a good feeling of this. Like, I mean, think about this. Here is something really heavy to lift. Really heavy. And here you are here. and you're going to push down on this. You're really going to push down hard to make this go up, okay? Now, you could push harder. You know, you could really push really hard, or you could do this. You could make this lever a little bit longer. So which would be easier to do? The longer one, yeah. But have you pushed any harder? No, it's the same force. That's because the turning force, the moment, it's not equal to F. It's not equal to the distance. It's equal to the force multiplied by the distance. So because the distance is bigger, it means there's more moment, more turning force. And you kind of have a natural feeling for this, you know? Like if you think about the door, it's easier to open the door at the handle than to try and pull it at the middle. You know, like if you had something here, you know, it would be easier to open the door from here rather than trying to pull here. And it'd be really hard to try and open the door pulling here, okay? So we understand that the distance should have an effect on calculating this. And of course the force should have an effect as well. So this actually makes sense. And what's the unit here? What's the unit? Newton meter. Yeah? Now we have to just be a little bit careful because it gets a little bit complicated if you pull at an angle. You know, if you don't pull straight, if you pull at an angle. So you can think about it like this. Let me try and draw it. Okay. You are pulling at an angle. So you could say that the moment is the force multiplied by the distance. But the question is, what distance? It's not this distance. Okay.
Plus the force?
Huh?
Plus the force?
Well, not plus the force, but rather
No.
this distance. Okay, because in my definition, I said you should use the perpendicular distance. Now, in this picture, that's easy because it was perpendicular. But if it's at an angle, you have to use that distance. Now, that's kind of messy, isn't it? Well, what you could do, or you could do this. You could take your force and calculate this, which you know is F cos theta, whatever, let's call that theta, okay? That's F cos theta. And this one here, F sine theta. And this one here, let's call this, okay, I don't want to call that D. I'll call that D. So you could use F sine theta multiplied by this distance D. Now, 99% of the time, that's the easiest thing to do because you know how to resolve, don't you? So you can take this into 2 and just use this one, which is perpendicular, and multiply it by this. Yeah? But then what about this guy? What happens to this one?
You're adding.
Yeah, you're thinking of adding it onto this one. Sadly not this. It's better though. It's a better thing to do. What do we think? Any ideas on what to do with the other one?
Just don't write it.
Closer! You delete it. You say, why can you cancel it? Well, you can cancel it because it passes through the turning point, and it means it's not important. Now, why is it not important? Well, think about this. If I go back to my door, if I pull here, I can open the door. Yeah? If I pull here, I can open the door. If I pull here, I can open the door. The one place I can't open the door is if I pull here. There's no amount of pulling that will make the door open if I pull at the turning point. Okay? So this force here can never make this turn. Never. Because it's pulling at the turning point. It can never make it turn. Okay? So in fact, you can actually delete it. It doesn't have any turning effect. Okay, do you understand this? See, so here, I can't open the door. So this force here is like this. Because it points to this point. This point is like that. And my arm is like this. So if I'm here, I can't pull it. I can't. So in the questions, usually it's better to use this formula because it's too difficult to calculate this, you know, because you'll have to draw this line backwards and then you have to figure out this distance. It's very messy. So the easiest thing to do is just use the formula f sine theta times d, where theta is the angle here, and then you forget about the cos part. It's not needed. You just use the sine part. The sine part is perpendicular. Okay, so it's a bit complicated. I don't know if you want to try and draw this. Let me redraw it actually. Let me redraw it. Okay, so you have two pictures. The simple picture, which is like this. So the moment is FD, okay, and the more advanced picture, which is like this. So this has two components, a piece this way, f cos theta, and a piece this way, f sine theta. So the moment here is f sine theta d. Okie dokie. Do we get the picture?
Just advancing.
Yeah. Got that? Yeah, continue. So, let's have a look-see. So a very particular common problem is this one here. We see this one a lot. This one is when you're driving your car. This one here is when you're cycling your bike. And this is a very special problem. It's called a couple. What does a couple mean in English? It means two. So you can see in the picture there's two forces. F and F. And here F and F. Yeah? The two forces are equal and opposite. They're equal in size and opposite in direction. They're the same distance from the pivot. Let's see what the turning force is. So let's picture the lid here. You want to turn it to open it. So in fact, what you're doing is this. You have a force this way and a force this way. Okay? And let's call this distance here, we'll call that capital D, for the total distance. Okay? Now, force here, will it make it turn clockwise or anti-clockwise? It'll make it turn anti-clockwise. And this one here? Also anti. Okay? So both forces are trying to help you turn it. Right, well let's see. How big is the moment here? So the moment from the first one will be the force. And what's the distance? Very good, it's a half the d, isn't it? Because it's only from here. And then what about the second one? What would it be? Again, the same thing, isn't it? So if you were to add them together to get the total, it would just be F times the diameter. Okay? So it's one of these multiplied by this is the total turning force. This is called a couple system. Sorry, Steve, I've just noticed right now you have pictures of naked men on your clothes. I've only just noticed that.
Yeah, people don't notice it, thank God.
No, I've been sitting here for 45 minutes. I've only just noticed
I wore
it.
this like 4 or 5 times.
Seriously? It's the 5th time I've seen it, and I've only noticed it today.
What? Half.
It's quite amazing, actually. All right, do you have that? Yeah. Yeah. Got it? Yeah. Okay. So that's a couple. So the definition. Well, actually, what would you say the definition is? How could we try and put this in a word? A couple is, what would you say? Two forces. Yeah. What else? Opposite directions. Yeah. Equal in size. And what's the purpose of these two forces? What are they trying to do? Look at both of these pictures. What are the forces trying to do? Yeah, turn in the same direction. So a couple is two equal but opposite forces, a distance d apart, that cause an object to rotate. Rotate is the word. But not move in a straight line. And the total turning force is Fd. Do you know this word, rotate? This is rotate. So I need to be a little bit more careful with my English. When I say equal but opposite, I mean equal in size but opposite in direction. Got that? Yeah? Okay. Right. So, here's our very first question. And you know what? I'm just going to draw it and you can tell me the answer. I'll make it something similar to this. Alright? Here is a car. and the car is stuck in some mud, and you're trying to free it. So you stick a little rock here, okay, and you get a big long stick, pole or something, and we'll say that it's 2 meters from here to here, okay, and you're able to stand on this. You can push it down with 1,000 newtons. Really push down hard. So I want to know, what is the moment here? Okay, so we can do this one together. What's the formula? Force times distance. And what's the force here? 1,000. And the distance? 2 meters. So this is 2,000 Newton meters of turning force. Which is a lot. So it's kind of like you've doubled your ability by having a 2 meter stick instead of just trying to lift it with your hands. So this is our first example, quite a simple example. If you can draw this, please. And, I think it's a good simple one to start with. Okay, did you draw that? Yeah? Right, next one now. It's really kind of the same thing. Multiply 20 centimeters by 100 newtons. I won't even bother with that one. I never put it in there. Right, here's a little bit more interesting one. So you have a steering wheel, and with one hand she pushes up with 5, and the other hand she pushes down with 5 newtons. What's this type of problem called? A couple, yeah. And the steering wheel, what's a small steering wheel? 30 centimeters? I guess that's about right. So what is the turning force? What is the couple here? So let's try and calculate this. You can tell me what it is. Got that? What's the answer? Siba, what do you think? Yeah, correct. But I don't think so. What did you get, Chow? 1.5?
1.5.
Yeah, 1.5 is what I thought. 5 multiplied by 0.3. Yeah. How did you get 0.15?
Because that converted wrong.
Alright, okay. Is that okay?
Yeah.
Alright. Oh, that's... Oh, I don't need actually that in there. I just need to delete that. Bum, bum, bum. One moment. Okay. Right, so let's see. Oh, for goodness sake. Okay. Yeah, so not really much to calculate in this lesson. I think you'll have an easy time with the questions. So if you can do these for 10 minutes, I don't even think it'll take you 10 minutes. Yeah? Oh yeah, well, obviously the length here matters, and we'll look at that in the next lesson. But I was only wanting to know what is the turning force from this guy. But yeah, you're right. In the next lesson, we'll need to work at this guy, and then it'll be like a minus to this, you know, because he's trying to make it turn anti-clockwise. But this one actually, he's pushing down, so he's trying to make it turn clockwise. So you want this force to be bigger than this force. So yeah, in the next lesson, I think we'll look at it in more detail. I think so, yeah. Let me put the light on for you. Whoa.